dealing with square roots for the rest of the year, radical expressions, some basic stuff involving numbers, some interesting stuff involving numbers, and as you can see, stuff involving variables as well and exponents. So radical expressions are any expressions that have a square root symbol in them. And just a vocabulary word you'll hear me use, a radicand is what we call whatever is living underneath the radical symbol. Quick note, while we know that the square root of 4 can be both positive and negative 2, because positive 2 times positive 2 gives us that positive 4, but so too would negative 2 times negative 2 give us that positive 4, we are going to, for now, focus on the primary square root, which is just the positive one. There are some rules here, and we'll get through them in several lessons, but to simplify a radical, the radicand, so what's underneath the square root symbol, must have no perfect square factors. I'll explain that in a minute. The radicand must not have a fraction, which means you cannot have a fraction living underneath of a square root. And there must be no radicals in a denominator. Now, to simplify, no perfect square factors, perfect squares. You may want to have somewhere written down just some of your common perfect squares. I would say the first 10 minus 1. 1 is boring, and it even says there other than 1. This should do for most of what we see. So what do I mean by that? The square root of 18. Well, we know 18 isn't in this list. It's not a perfect square. And like we could grab a calculator and get a decimal, but that's not what we're trying to do. The rule is that the radicand, the thing underneath the square root, can have no perfect square factors. And 18 is hiding a perfect square factor. So what is a factor? You got to think way back to like third grade. Third grade is probably when you were first introduced to that vocabulary word, a factor. A factor is basically something that you multiply. So my question is going to be, do we have any multiplication statements that make 18 that use one of these perfect squares? It doesn't have to be multiple perfect squares. It just has to use one of these. And 18 does in fact have a statement, a multiplication fact, that makes use of one of our perfect numbers, which is 9. 9 times 2 is 18. Now, what's cool about this is with multiplication underneath a radical, with multiplication underneath a radical, if something is a perfect square, we can bring it out of the square root as its square root. What is the square root of 9? It is 3. The thing that is not a perfect square, which is the 2, must stay behind. Okay. Simplifying radicals often comes down to an idea of finding everything we can to get out of the square root. 3 root 2 is the simplified form of root 18. So with numbers, this list is going to be your most useful asset. With variables, it's actually quite simple. I'm just going to actually write this down. Even exponents are perfect squares. Any even exponent is a perfect square. How is that true? Well, remember, the square root of x to the fourth. So something times something, or something times itself, makes x to the fourth. Think back to chapter 7. Wouldn't x squared times x squared be x to the fourth? We add the exponents. Following this through, x to the third times x to the third would be x to the sixth. X to the fourth times x to the fourth would be x to the eighth. If you have two copies of the same thing, x to the same power, you notice we just keep getting even exponents. So what is the square root of x to the fourth? What times itself makes x to the fourth? That's x to the second. Our next radical has a fraction. And underneath that radical, neither one of those two numbers, 2 or 72, is perfect. But that fraction does simplify. Both 2 and 72 are even. So we can begin this problem by cutting both in half. Half of 2 is 1, and half of 72 is 36. Now, and I will remind you, there is an invisible 1 in the front of this list of perfect squares. It's boring. That's why I didn't write it. Both of these numbers now are in my list. So the square root of 1 over 36 is actually just the square root of 1 over the square root of 36, and we know both of those. The square root of 1 is 1, and the square root of 36 is 6. Back in the first example, I made a point of saying and repeating that we are allowed to bring perfect squares out through a multiplication statement. And I stressed multiplication. That's because addition doesn't work. So what are we going to do here? Well, we're actually going to turn this into a number. So 3 to the second power is 9. 4 to the second power is 16. Because addition stops me unless I can factor it, which we're going to get to in a second. With just numbers, I have to work them into a single number. 9 plus 16 is 25, and thankfully 25 is in my list. 25 is a perfect square. Square root of 25 is 5. Now here we have ourselves a trinomial. We just spent a chapter factoring, and you see the word factor on this page. We're talking about factors. Let's try factoring this. Now this is a basic trinomial. There's nothing in front of the x squared, so we don't have to go crazy. We're looking for two numbers that multiply to make 16 and add to make 8. Those, of course, are 4 and 4. Two copies of 4. Well, that's something times itself. That is the square root of x plus 4 quantity squared. And just like subtraction is the opposite of addition, and they would cancel each other out, like adding 6 and subtracting 6 does nothing. Multiplication and division are opposites. If you multiply by 3, then divide by 3, you don't really do anything. Squaring and square rooting are opposites. So if I take the square root of something squared, they don't do anything. They cancel each other out. They leave behind whatever was underneath the radicand in the parentheses that was to be squared. The square root and the square just gone. In the next example, we have the square root of x to the fourth, y to the third. So we have multiple variables, and with variables, we're looking at the exponents. And we want even exponents preferably. So we kind of have one here, and we don't have one here. We do have an even exponent on the x. So that's going to be just fine. We'll get him out in a second. The y has an odd exponent. So it can't come out as it is. But that doesn't mean that we can't do some simplifying. The idea here is we can break up y to the third. Y to the third doesn't have to be y to the third. He can be y to the second times y. Okay, Okay, there's now 3 items underneath this radicand, but two of them are in fact perfect squares. So both of them get to come out as their square roots. X to the fourth has a square root of x to the second, half of the exponent. Y to the second has a square root of y to the first, half of the exponent. I'm not going to write the exponent of 1. That extra y, though, is still trapped. We can't get him out. There's no way to get him out. He has an odd exponent of 1. He has to live there. The best we can do here is x to the second y root y. Another fraction. Cannot simplify this fraction. And honestly, I don't want to yet. And here's why. If the denominator of my fraction is perfect, then I want to break it up and simplify each portion of my fraction separately. The square root of 5 is the square root of 5. The only way you can make 5 is 5 times 1. There are no perfect squares hiding in it. We're done there. But the square root of 9, well, that's 3. Root 5 over 3. Now, something I want to point out. Let me just get a little overboard here. I don't know this, what I just wrote. If you give that to me on a quiz or a test, I'm not going to be entirely certain if the square root is on the 5 or the whole fraction. Okay. Your neatness is important. Notice in how I wrote my answer, I made sure you can very clearly see that the square root is strictly on the 5 in the numerator. The square root is part of the numerator of the fraction for sure. Make sure you do that. If you have a radical in your numerator, that's fine, but make sure I can tell that it only belongs in the numerator. Next example, we have root a to the 5th over 81a. And we're close to being really good. Like, that denominator is almost perfect. 81 is in my list. But the a, just a single boring a, means right now the denominator is not perfect. Because that single boring a has an invisible exponent of 1. It has an invisible odd exponent. Darn. Okay. If our denominator isn't perfect right now, we can probably simplify the fraction and make it perfect. And this relies on you looking at this and recognizing, hey, I have a's and I have a's. So I can simplify. Division rule. If I have a divided by a, I can subtract the exponents. The 5 from the numerator minus the invisible 1 in the denominator gives us a to the 4th over the 81. And there's no more a in the denominator. And now our denominator is perfect. So we can break this up as root a to the 4th over root 81. And these are both perfect. We're going to get a squared over 9. Next example, we have root 80 over 25. And while you can simplify this fraction, you shouldn't. Because its denominator, the 25, is perfect. So we're going to break up this fraction into root 80 over root 25. And let's see what we can do. Now we know 25, it's in the list. Denominator's already going to become 5. Cool. The numerator, however, 80 really feels like it should do something. And your first instinct is going to be to say 8 times 10. But look at our list up at the top. Our 8 or 10 in that list. They're not, so they don't help me any. So 4 is in the list. 80 is 4 times 20. But 20 is 4 times 5. If 80 is 4 times 20 and 20 is 4 times 5, then 80 is 4 times 4 times 5, or 16 times 5. The biggest perfect square hiding in the number 80 is 16. Now let's simplify what we can and leave behind what we can't. In the numerator, the square root of 16 is 4, so we can simplify that. But we cannot simplify the square root of 5. It's left behind. In the denominator, the square root of 25, that's perfect. It is 5. You cannot simplify the two 5s in this answer. One of them is protected by a square root symbol. And square root symbols are kind of like a barbed wire fence. Unless you can get yourself out from under it, you can't work through it. Can't get root 5 out from under it. So those 5s cannot interact with one another to simplify. We're done. Last example, again, a fraction. Our denominator is perfect. So let's go ahead and break him up into root 4x to the 5th over root 9. Now the 4 and the 9, the numbers, are perfect. The x to the 5th, odd exponent, he's not perfect. So we're going to have to break him up. Anytime we're doing square roots and I have to break up an odd exponented variable, I'm literally going to do it as the variable with an exponent that is 1 smaller, so 5 minus 1 is 4, and then the variable itself. Always just going to be 1 smaller. And now let's look at our perfect squares and get them out, and leave behind that x to the first power that has an odd exponent. Square root of 4 is 2. Also in the numerator, the square root of x to the 4th is x to the 2nd. We already know that square root of x is left behind because he has an odd exponent, and you can't make one any smaller. In our denominator, the square root of 9 is 3. And take a quick look at your fraction. We have a 2 over a 3. You can't simplify that. We're done here.